Yes, and the term challenges here is overloaded, by the way. That's something for you to think about, but it has several meanings. So maybe a quick raise of hands, like who of you has attended actually the DIMACS workshop online last year? Okay, I was hoping that would be a bit less because I'm sorry there will be some overlap, but maybe that means I will go through that part a bit quicker. But on the other hand, right, a bit of recap always helps things to settle in. And so this presentation will not be my most technical presentation, but it will be a bit of an overview, taking you along, let's say, on my personal journey, my tour, let's say, over the past few years working on routing problems, but it also serves, I think, as a nice introduction on the different challenges that this workshop is also about. But I want to start with a bit of my own research. So this is actually my PhD research, which was about learning to solve routing problems. And after just hearing Andreas talk, maybe I should have called it learning to repeatedly solve related routing problems. That would be more accurate, but also too many R's, I guess, in the title. So let's stick with the learning to solve routing problems. But this is really an example of the end-to-end method, let's say, which Andrea presented. So my first paper, actually, that I published as part of my PhD, was called Attention, Learn to Solve Routing Problems. So attention referring to attention mechanisms in machine learning, which is sort of the breakthrough technically that nowadays also make models like ChatGPT possible. But anyway, the idea of this work is that we have what I like to call the traveling scientist problems, right? So let's say you're visiting a conference, which is a bit bigger than this workshop, and there's like a number of posters that you want to visit, right? You better make sure you don't waste too much time wandering around because, right, you can spend that time better. So the question is, what is the shortest path, right, that you can take to visit all these different locations? And what we show in this work is that actually you can train a machine learning model, a deep neural network, that just takes as input, let's say, an instance, and as output it directly produces the solution to this problem. So this is what we have seen in the previous talk. And this is really an example of an end-to-end method. And the way it actually works, if we, I have a nice visualization here, it constructs a solution one step at a time, right? Because there's certain global structure, right? You want to make sure that every node is visited and that you return to the starting solution, and you can really efficiently enforce this by just like one step at a time predicting the next customer. This way you can guarantee that your machine learning model will not predict to go back to a customer that you have already visited, because you can just remove it from the set of options, basically. And what you see here, you see this small gray bar. It represents, let's say, the probability the model assigns to moving there next. So you see very often it's very confident. It always puts all probability at just the next place to go. And with this, it can construct actually not an optimal solution, right, but it can construct a reasonably good solution to this problem. Typically, we get to like few percent of optimality for like 100 node instances. And I think if I would challenge you, I would give you this dots on the paper and let's draw a tour. I'm quite confident that this model will do a better job than you. It's quite difficult to do that, and it does this really well. So in that sense, it's superhuman performance. I should maybe have published this in Nature with some big, but anyway, I think it's quite nice that we can show here it's not optimal, but we can get really interesting like heuristics that we can actually learn completely from scratch. This doesn't take any example information, it just takes instances, and it learns by reinforcement learning, by trial and error, to generate these tours in this constructive way. And we also show that you can't just do this for TSP, but you can also do this for like routing problems, and we showed for some different variants. But obviously this has its limitations, right? Once you make a certain partial tour, you can't change it anymore. So this model makes mistakes, doesn't give you the optimal solution. And so something that we did as follow-up work was actually to make more of like a hybrid approach where we combine indeed machine learning as part of an OR algorithm. And so here we built on the classic dynamic programming algorithm. So probably most of you know the dynamic programming classic algorithm for the TSP, and there's also dynamic programming formulations for VRPs. And what we show that you can actually make them into a heuristic, right, if you just restrict the search space for your dynamic program. So you don't consider all options, but you limit somewhat the search space, and then in this paper, we show that we can use a machine learning model to make actually predictions on the set of edges to identify like promising edges. So in this case, it's based on supervised learning. So we just train this model based on example solutions to predict what edges will be part of an optimal solution. And that means that if you have like a new instance, you can just make this prediction and you get really like a sparse instance out of that. You can prune like 95% of your edges and really focus the search and then your dynamic programming formulation only on this promising subset, where you can also use these edges then to score actually partial solutions during your search algorithm. And so if you want to read more about that, then it's all in my PhD thesis, I would say. Forgive me the joke, it's not related to this, but I reused the slides. But so that was about my PhD research, which is on learning for vehicle routing problems. And so as the next stop, let's say in my tour, I want to talk with you about the DIMACS challenge. So if you've seen my talk the last year, then go ahead, take a break, and I will call you out with the third stop. But I think it's nice to have this as a small recap also for this workshop this week. So we took part in the DIMACS challenge, especially in the track for the vehicle routing problem with time windows. And that is a vehicle routing problem, right? But it's limited in the sense that we have different vehicles with limited capacities. And every customer, in addition to like the capacitated vehicle routing problem, has a time window in which it must be served. Or it means that at least service takes a certain amount of time and must start within the time window. And the objective, at least in the case of the DIMACS challenge, is to minimize the driving distance or the duration, depending on how you view. This is the same. So we do not minimize, let's say, number of vehicles or waiting time. It's purely minimization of distance. And so I proposed that Ortec actually to join this challenge, since we're a company that builds route optimization software. But since this is like a rather pure problem, it's quite different from what we solve in practice, we really decided to build an approach which is specifically efficient for this problem. And so I'm going to share with you let's say, the winning recipe for this challenge, because Eduardo has shown it during the introduction that we actually got the first place in the VRPTW track. But so what we did was we built on the open source state of the art. So for this, I really have to credit Thibaut for open sourcing a very nice implementation of the hybrid genetic search algorithm, which is like the state of the art for the vehicle routing problem. Or the capacitated vehicle routing problem. And so then actually we just re-implemented also a very nice paper by Thibaut. So pretty much you should deserve all of the credit, you could say, for this. And we implemented it on top of this hybrid genetic search algorithm. So there wasn't a good open source implementation for that at the time. There is now. I will get to that later. And then with some colleagues, I got enthusiastic about this. We basically did a hackathon. So I put them all together. This was during COVID times, so not in a physical room, but in an online room, you could say. We sat together for a week. We did a lot of hacking to make this all work. Some mixing, yeah, okay. And so in the end, we devised this algorithm, right? We let it run for 3 days because we had to like evaluate it ourselves. This was the way the DIMACS challenge was set up. And then we submitted the solutions and we had to wait for the results for some time. But then actually it turned out that, well, this worked pretty well. We got the first place in this competition. And so it was all made possible, you could say, by just building on the hybrid genetic search algorithm, which is like, I'm a big fan of it by now. I think it's very powerful and elegant algorithm. And, you know, since I think, Thibaut, you liked the previous explanation, I want to do it for you again, but then live this time. So, but I think it's also nice because I think other people have built on this as well. For who is not familiar with hybrid genetic search, I'm going to do like, well, relatively simple explanation. So this is a genetic algorithm, and in a genetic algorithm, it means we have a population, or sometimes we call it a pool, right, of solution. And this very nice pool. It's not like the one in the hotel, I think, which is non-existent, apparently. That was a slight disappointment. Anyway, it doesn't matter. So we have a pool, right? We're going to initialize this pool with initial solutions. So we have some heuristic strategy which we can create to use to create initial solutions. And very important, I would say, is we don't only work with feasible solutions. We also allow feasible or solutions to be infeasible during our search process. This is basically to smooth the search problem, to make it more easy to find, let's say, the global optimum. And so in every iteration, we're going to do what is called a binary tournament. Now here it can get a bit nasty, let's say, but what we do is we get basically 4 solutions out of this population. We're going to draw them uniformly, and so we're going to pair them up in pairs of 2, and we're going to make them fight. That's why it's called a binary tournament, right? And so the one is going to say like, hey, I'm the better solution, right? I should be the one to reproduce, but then the other one is going to say, yeah, but I'm more diverse, right? We should take that into account. You don't want all the same solutions, even if they're very good, right? You want to maintain a certain diversity in your population in order to be able to find a good solution. So these solutions are going to fight, some are going to win, some are going to lose, and in the end we find 2 solutions that we are going to combine to reproduce, right? That's the whole point of a genetic algorithm. And so this can be 2, let's say, infeasible solutions from the pool. It can be 1 feasible, 1 infeasible, or it can be 2 feasible solutions. I'm open-minded in this respect, but anyway, they're going to do what I like to call the dance of romance. And then what do we get? Okay, come on, people. Okay. Baby solutions, indeed. So, right? So the idea is we combine some solution in this pool, right, through this mechanism, this binary tournament, which makes sure that we take into account a bit of the diversity, a bit of the quality, let's say, and we get new solutions. Now, if you do this crossover, right, they're just very helpless little bad baby solutions. So we have to educate them and make them into like full-grown solutions. So we use a local search algorithm to basically repair everything we get from this crossover. And so in the end, we get this like full-grown, locally optimal solution, and we're going to insert that back into our pool. Bam, there it is. You saw the animation? That's just standard PowerPoint. But anyway, right, this could be, because we smoothed this search problem, right, we relax some of the constraints, we get an infeasible solution, but we want feasible solution in the end. So not always, but we flip a coin, and let's say 50% of the time, we're going to run an additional local search procedure where we're trying to repair this solution. So we're going to increase the penalties for violations of like time windows or capacity constraints, and then we will hopefully find a feasible solution, then we will put that back into our pool as well. And so this is basically how the hybrid genetic search algorithm works, and then if we repeat that for a number of iterations at a certain time, our pool just gets too crowded, right? You want some space in there. So we're going to make sure that we are going to remove some solutions from our population or our pool. And this is then based also on the criterion taking into account the diversity, let's say, and the quality of the solutions, all with the goal of having, like, let's say, a set of solutions that somewhat covers your search space, but is also of high quality, right? All locally optimal solutions. Okay, so we remove them, right, and then we repeat this process for a number of iterations, and in the end that will make us find a very good solution. And so now what did we do as part of this challenge? On top of this hybrid genetic search algorithm, we added a number of additional initialization strategies. I have to say Niels removed them later for the next challenge. But we found them to help, so it depends also a bit on the data set, I guess, which you're testing. But we added an additional, let's say, crossover operation to combine solutions, and we improved this local search, right? So we added time window support, but also we did a lot of optimization, some additional neighborhoods. And in the end, this just made it all together work really well, and we also found some new best-known solutions with that approach. And so to summarize, let's say the key ingredients that make this algorithm work so well was this hybrid genetic search, but with some specific components. So we did the specific route exchange operator to combine solutions. We use this like implementation of dealing with time windows in a way that is very efficient, let's say, to compute and to evaluate certain moves. We implemented the swap star operator, which was recently introduced by Thibaut, but for the vehicle routing problem with time windows, it's actually approximate. So the idea of the swap star is to exchange nodes between two pairs of routes, but then reinsert them, let's say, in the order route in the best position. So if you don't take into account time windows, you can sort of like optimize or cache some of the computation. You can compute this exactly, but with time windows, we made an approximation for that, but that worked quite well still. And then we did a lot of optimization. So we did like integer computation instead of floating points, some like pre-checks, caching, and we did a lot of parameter tuning to make this work well. And so that was what enabled us to do this DIMACS challenge. And then I thought, okay, it's very nice right now that we have this algorithm, but I really felt, let's say, the urge to like continue, maybe have another competition the next year, so we could all build, let's say, on what we now know is the best solution for that. And that's why actually together with some of you, so also with Thibaut and Kevin who are here, I proposed to make a follow-up competition, which was the Euro meets NeurIPS vehicle routing competition. And this was slightly different, let's say, from the DIMACS challenge, in the sense that we really try to focus a bit more around machine learning, because like Andreas explained, I think there's a lot of potential to use machine learning-based approaches, maybe also like related to, let's say, vehicle routing optimization. So for example, predicting like driving times or like the input of your problem, but also to optimize, let's say, your algorithm itself. And that's why we try to build this competition and really try to bring together people from operations research and machine learning community. And to make this, let's say, more tempting for machine learning based approaches, we also introduced the dynamic variant, which Thibaut already mentioned. And so a bit of the motivation, it is because I observed like that we have people working on routing problems in the operations research community, but also quite a lot in the past few years in the machine learning community. But we see that these people take different perspectives, right? So our researchers, they tend to use like relatively simple machine learning methodologies, I would say. Not like the big scale deep learning architectures that are possible, but also in the machine learning community, you see that very often some baselines in the OR community are disregarded, right? So simple heuristics are compared to, and then sometimes rather strong claims are made about this. So I really felt the need for like an independent evaluation of, let's say, people from OR and machine learning communities from different types of methodologies on the exact same problem. And so to do this, we sort of try to bridge, let's say, this gap between the communities, and so really have this competition, which was actually launched at the Euro conference, and it was actually finished at the NeurIPS conference, which is like the biggest machine learning conference. And so that's a bit of the how. So we brought really, I would say, different communities together. Also from Ortec, we tried to add real data to make the problem a bit more relevant, although in the end we also had to simplify it, of course, quite a lot to make it possible. But we also we provided actually this winning solver, right, this hybrid genetic search as a baseline, such that both communities, let's say, could build on the state of the art, and we could really set like a high bar for making like improvements, which would really improve on that. And we encouraged, let's say, the use of machine learning approaches by having this dynamic problem variant. I will explain that in a second, but also by allowing people to use a GPU. So making this advantage that you could use machine learning based approaches, which is like typically quite difficult, I would say, for classic algorithms, whereas they are available nowadays. And so to actually improve the engagement during the competition, I really wanted to have a code submission platform where you could submit, like during the competition, your solutions, and you could really see how other teams were doing as well. You could have a live leaderboard, and I have something to show about that in a bit as well. And so some example of the data, it's a bit like in practice, you don't have the pretty distributions that you might expect. And so for this dynamic variant, the way it works is that we actually sample, let's say, requests that need to be served from, let's say, this data that we have. So we assume that this is a fixed customer base, a bit like the setting that Andrea has also shown, and that, let's say, every hour of the day, some of the customers will order maybe for later today or maybe tomorrow. And then I have to make a decision if I would, let's say, dispatch those customers now, if I would put them in a truck, or maybe I would save them because at a later point I would have maybe some new customers that I can combine with them. So there was really this dynamic aspect where it's like not purely combinatorial optimization, but you also had to anticipate a bit on the future, let's say. And this was then, we provided an environment, let's say, that would then generate these new solutions that the solvers could interact with. Now for some statistics, so in the end we had 150 teams registered for this challenge, where I think we made it quite challenging because a lot of them also dropped out. So in the end 50 teams, which I think is still quite impressive, submitted a solution. And to be clear, to participate in the challenge you had to participate, let's say, both for the static and the dynamic variant. We really wanted to test, let's say, the universality of the approaches. Although we saw that most people really focused on, let's say, one of the problems. But in the end, we had like 800 submissions, a lot of people on the Slack, and a lot of messages there exchanged. And the nice thing of this code submission system was that we could have a public leaderboard during the competition. So it ran for a few months. And so we steadily saw, let's say, the number of participants increasing. And here you can see, like in bold, I marked the top 10. So the finalist teams, you can really see like how they ranked. So some teams, they really took some time maybe to make it to the top. And I also heard from a lot of teams that this was really helpful to sort of be motivated, like pressing the refresh button on the leaderboard and then seeing another team do better. That really, I think helps motivating and also know what to aim for in terms of the results during the competition. And so finally, the top 10 of this leaderboard, then those teams became the finalists. And in the finals, we evaluated their solvers actually on a new test of instances. So during the public leaderboard, those instances were also secret. They were not public. But we wanted to, like, say, test it more thoroughly on more and a bit different instances, and also with longer run times. And then finally, at NeurIPS, we announced the results. And so this is not a surprise, this is already publicly known, right? But we have 3 teams here in the top 3, and actually all of them are here this week. We'll also present their approaches. And so, well, this time in person, congratulations also for doing so well in this competition. Now, for the question of what did it bring? So we saw that a lot of teams actually built on the hybrid genetic search, which I think is very good because I think it's a very powerful algorithm and that really pushes the state of the art. On the other hand, it's also, maybe we should think about like how can we also encourage different type of approaches, because we risk getting into a local optimum, let's say, as a community. But we saw at least that a lot of people made improvements to that. But especially for the dynamic variant, we only had some very simple baselines, and the teams have really made quite interesting contributions that we will see talks about as well. So especially I would want to mention, let's say, the price collecting approach by Team Cleopatra, which basically integrates a machine learning algorithm to sort of predict not like which customers you should deliver, but a certain value for each of the customers, and then use like a price collecting formulation of the vehicle routing problem to then dynamically select which ones to integrate. And so I think this is a really elegant example of how we can use machine learning and integrate it with an OR algorithm, and that it actually works. It outperformed, let's say, some of the other teams did more of like stochastic program or like simulation-based approaches, and the machine learning-based approaches were able to outperform this. And so we wrote a retrospective on this, which is pending review. And one thing that I think is very nice that came out of this, but I shouldn't take the credit for it because like Niels did a lot of work with this, also together with Leon. But we're working on a PyVRP, which is sort of the evolvement of the hybrid genetic search implementation that we open sourced after the DIMACS challenge as part of the EuroNeurons challenge, now into like a fully fledged Python package to really make it easy for people. You can just pip install it and it works. So that's quite easy. And from the Python level, you can like set up your problem, enter the data, but you can also customize the algorithm. So you can like define, let's say, the operators which define your local search neighborhood. You can define your granular neighborhood. You can do like population management. You can run the local search as a separate component. So it's really, the idea was that we make it sort of flexible from the Python level, also to make it much easier to do things where people could use machine learning based approaches, for example, to define neighborhoods, to do like parent selection and those type of things without needing to embed that into like high performance C++ code. So finally, if I have a few more minutes left, I want to mention something about vehicle routing that we do at Ortec. So Ortec, we're a company, we do like a lot of different types of optimization software, but a lot of route optimization for like customers all over the world. And for that, we basically have sort of like highly efficient Dijkstra implementations for doing like one-to-one routing. But on top of that, we do like route optimization. 3 seconds, minutes, hours, minutes. Okay. So and with that, we also face a lot of challenges, let's say, of solving optimization problems in practice, because like data is not always perfect, right? But also as input, let's say, for your vehicle routing problem, you need to know like the distance matrix, right? If you have 1,000 customers, you need to know for 1 million shortest paths computations, and it's also time dependent, right? So how can you compute that efficiently? How can you get like this time dependent aspect also in your route optimization problem? But we have to do with like driver legislation, some fuzzy constraints, like some customers, they want like pretty routes. You know, as a mathematician, don't ask me why that's relevant, but it's important, let's say, and there are all other types of things that we need to consider. One thing I would specifically like to mention is that the way we make a plan, right, is not the way it's always executed. Like the driving duration, it varies in practice, right? So something like a hard time window constraint that works during planning, but when you execute, it just means that your probability of being late slightly changes. So in practice, I would say it's always a smooth problem, right? You have a smooth objective, and in that sense, there's a trade-off. But it's not just like a solution is feasible or infeasible, but it's like more likely that the execution will be feasible. And there's a trade-off, like how much slack do I put in my plan, let's say. And so with that, we have to take into account, multiple objectives. And I just want to say, if you're interested in this type of problems, or like maybe connecting your research to a bit more like things observed in practice, then feel free also to reach out to me, and well, we can discuss ways maybe to collaborate or provide data. And that was pretty much. I hope I finished in time. Forgive me, this is just in the corporate slide deck. Okay. So.